Okay, everyone, welcome back to CSE 373. Today we're talking about one of the coolest algorithms that we'll learn in this course called Dijkstra's algorithm. It's going to be solving this thing that we call the weighted shortest path problem. But before we dive into all of that, I want to start with some announcements and then talk a little bit about reviewing what we learned about graphs so far. So, Project 3 is going to be due Wednesday, November 18th. Do note that this is a later deadline than originally published. I sent an email talking about how we're extending the deadline a little bit for Project 3. But again, do remember that Project 3 can be a little tricky, particularly when it gets to that change priority and contains. Everything before that should be very reminiscent of what we talked about in lecture. And we mentioned that for Project 3, change priority and contains can be a little tricky, and you almost definitely will want to use another data structure to help you solve those problems. But do remember, in terms of a development strategy, don't worry about the efficiency at first. Worry about that later, and then try to figure out what parts are slow before trying to speed that up. In terms of another announcement, we're going to be publishing exercise 3 Friday evening, and it is due the following Friday on November 13th. This exercise will focus on graph problems that we've been talking about this week. So working with graphs, analyzing them a bit, but do note that the exercises start ramping up slightly in difficulty now that we've kind of covered so much in this course. So now we can start taking the things we've talked about earlier, like algorithmic analysis, and applying them to more complex situations like with graphs. So we do recommend that you start this exercise early, or at least take a look at it so you have an idea of what kinds of things we're asking, and so you can get a head start on that. Now, whoops, wrong direction. So now onto the things that we want to talk about today. So today's learning objectives are going to be to have you describe the weighted shortest path problem and explain why breadth first search doesn't work to solve it. We want you to trace through Dijkstra's algorithm on a graph showing intermediate steps at each step to implement Dijkstra's algorithm in code. So we're going to kind of talk about what this algorithm is, and we want you to be able to implement it on Project 4. So it's okay if you can't implement it after today. Then we want you to be able to evaluate the inputs to and any modifications to Dijkstra's algorithm for correct behavior and efficiency based off some algorithm's properties that we're going to talk about. And then we want you to be able to synthesize code to solve problems using DFS, BFS, and Dijkstra's traversal. The idea being that we mentioned last time that DFS and BFS in particular are just traversals. You can use them as part of any algorithm to solve a problem with graphs, and we're going to practice that a bit. So the first thing I want us to do in this video is talk a little bit about review. So last time we introduced this term depth first search, DFS, and breadth first search, BFS, and these algorithms were used to traverse a graph. DFS kind of picks a choice, chooses a node, and explores all the way to the end before coming back and revisiting other choices, while breadth first search, BFS, does the opposite approach, where it kind of explores things layer by layer, exploring all nodes 1 away before all nodes 2 away, and so on. Now, one thing to highlight is that DFS and BFS are just techniques for iterating. Think of them like a for loop over an array versus a while loop over the array. They're both just techniques to iterate. You can use them in different contexts to solve different problems. So a lot of times when you're trying to solve a graph problem, it will just involve using some modification of DFS or BFS to solve the problem at hand. In terms of BFS in particular, to highlight that point, one of the things we talked about last time was using BFS for shortest path. So last time we talked about the unweighted shortest path problem, where we had a graph with edges that didn't have any labels. And we used BFS to find the shortest path in terms of the fewest number of edges to get from point A to point B. And we described it's just like BFS, kind of using this expanding perimeter going outwards, except we also want to keep track of kind of what's the shortest path so far. So we used 2 extra maps to keep track of information. One called edge2 that keeps track of the edge we took to get to this node, and dist2 to keep track of that shortest distance. All the rest of the code is basically the same as just breadth first search, except we're keeping track of which node we took to get here and what that path length was. And so we walked through example. I'm going to run through a little bit quickly. We started with our start node. We set its distance to that node by definition will just be 0 because it's 0 edges away from itself. We mark it as visited. And then we add all of its neighbors to our queue if we haven't visited them yet. Now, when we add them to our queue, we're going to associate them in these extra maps as storing the information to get there. So we'll say to get to this node, we took this edge from A to B to get to B. And the distance there is going to be the current distance to get to A, in this case 0, plus 1. And we just keep doing this for each node. And then we just repeat this over and over again, adding their neighbors, saying the edge we took to get here was from B to D. So we store that in our edge 2 map. And then the distance 2, we increase that value by 1 because it's one extra step. This all works all well and good because we're counting the number of edges we take. So every time we hit one of these nodes, because we're using a breadth first search, we know it's that shortest distance to that node. And so we can keep going until the end of the graph. Now, one thing to mention is that this edge 2 map is storing extra information that lets us reconstruct the path from it. So this edge 2 map stores what we call back pointers. It's not necessarily part of the graph. It's just keeping track of which edges we took so that we can reconstruct our answer later. Because what this breadth first search for shortest path produced is what we call a shortest path tree. It tells us exactly for any node in the graph what's the shortest path to get to A. Now, because we have that information, we can answer this shortest path problem from A to anywhere else in the graph. Which is a nice thing that you can kind of just run this one algorithm and build up the answer to any of the problems for nodes starting at A. Now, this tree can be built up or reconstructed from these back points, from these back references. Because you could say, oh, if I want to find the shortest path from A to D, I start at D, follow the back reference to B, follow the back reference to A, and then you kind of reverse that to figure out the path A, B, D. This property of building up a tree of kind of the results for the whole graph, this kind of shortest path tree, is very common for most of our shortest path algorithms, especially the one that we're going to talk about today. One thing I highlighted is that if you, in some circumstances, you can just return early. So if you're trying to find the shortest path from A to D, once you reach D and add the answer, you can just return right away. But sometimes it's really helpful to build up this whole tree, kind of pre-compute information, and then use that information later. Now, what I want us to talk about for the rest of lecture is kind of some new stuff of trying to solve this problem of what we call weighted shortest paths. So as a kind of a bit of context of what we just talked about, is last time we introduced breadth first search and depth first search, and we used either of them to solve the ST connectivity problem, the problem of figuring out, are these two vertices connected? Is there a connection between them? We then kind of upped the difficulty a little bit with this unweighted shortest path problem, where we're trying to find the shortest path between between two given nodes, such that that path had the fewest number of edges. And our solution there was using a modified breadth first search that kind of store this extra information for the shortest path tree. Now what we want to tackle today is what we call the weighted shortest path problem. And the idea here is we're going to be given a weighted graph. And what we mean by weighted graph is a graph that has edge labels. And those edge labels are numbers, signifying the cost or the weight of taking that particular edge. And now we want to find the weighted shortest path, which tells us what is the sequence of edges to take such that it minimizes the sum of the weights. Notice, very importantly, we have now changed the definition of what shortest path means. In the unweighted shortest path problem, we said that the shortest path was the path that had the fewest number of edges. And now we're saying the shortest path is the path that has the set of edges that with the sum of their weights is smallest. That's changing the problem a bit. So we're going to probably need to change our algorithm to account for this. Now, why won't we just be able to use BFS here? Well, let's think of an example. So assume we're back on campus. Suppose you're at Meany Hall and it was about lunchtime and you're trying to get to the hub as fast as you can to get some of that sweet, sweet Pagliacci pizza. Now, sometimes I do this because I'm curious, look at Google Maps to try to find like what's the fastest route, but maybe you can try to do it in your head. You could just look at a map and try to figure this out. What we could imagine is representing this map as a graph, where nodes are things like buildings or street intersections, and edges are roads or walkways. And you can imagine it being a labeled graph because maybe each edge, each road, has the amount of time it should take you to walk it or bike it or drive. And our goal here is that if we have this graph of campus and your starting point, and we want to get to the hub, find an algorithm that will find us the shortest path there. Now, the reason BFS might not work here is imagine Stevens Way, which is a very long kind of continuous road, was represented by one edge between Meany Hall and the hub. If we were to run BFS, it would tell us to take that edge, even though the cost of walking all the way around Stevens Way is a lot larger than taking those 3 separate edges. The reason BFS is not going to end up working here is because BFS cares about minimizing the number of edges taken. It doesn't care about the edge weights. So we might need to change our algorithm a bit to account for this. Now, before we talk about that, let's revisit BFS for the unweighted graphs and kind of understand why it worked in the first place. We have a key observation for why breadth first search works for these unweighted graphs, which we call the first try phenomenon. Now, I'll mention this is not a common term. If you look it up, you probably won't find anything about it. We use this term here because it kind of accurately describes something without using a super complex terminology. The idea of the first try phenomenon is, first, BFS will only enqueue each vertex once. So it's going to be efficient. So you're not going to be visiting a vertex multiple times. And additionally, once we enqueued a vertex, we know the final path to that vertex. We never have to reevaluate its path and figure out, what if there was a shortest path like later on? So what I mean by that is, for example, the reason this works is because BFS always processes the closest vertex first. So when we go to enqueue a node, we're always looking from the perspective of the closest node. So for example, if we're trying to find the path from A to C, we're always going to take this A to B to C path, not the A to D to E to F to C path, because we always enqueue nodes based off how close they are. So we'd always include B and D together. And because we're using this breadth first search, we always will dequeue B before dequeuing E, F, and getting to C. That's kind of the key intuition here for why this works. So why doesn't this work when we're thinking about weighted graphs? Well, part of it is because BFS doesn't care about the weights. It doesn't look at it. So if we look at that exact same graph, but add some edge weights on there, BFS would tell us, take A to B to C because that's the fewest number of edges. However, if you sum up the cost of taking that route, that's something like 300. But if you went the long way around in terms of the number of edges, from A to D to E to F to C, well, each of those edge weights is only 1. And so you would only incur a total cost of 4. And so BFS is not able to find this. Now, the key observation here, though, is that the first try phenomenon still holds. Like, we're still operating under this assumption that when we enqueue a node, we know its shortest path. But it turns out that that shortest path is not necessarily going to be correct. It's not going to be the one we wanted. BFS breaks because we're no longer processing the closest vertices first. Remember, now we're in the weighted graph problem, we define closeness based off the sum of the edge weights along the path. If we just use plain old BFS, we're just taking the number of edges as our metric. We're not taking these edge weights. So we can't rely on the first path found being the best anymore. So if we're trying to solve this, one potential idea is to try to change our weighted graph into an unweighted graph such that we can then run BFS on it. This is going to be a technique of a more general type of something that we call a reduction. taking a problem and translating it into a problem of another type that we know how to solve. This idea of a reduction is something that we're going to be talking about more later in the course. I'm not going to spend a ton of time talking about these reductions now, but I want to spend a little bit of time talking about them because this is a good example to bring them up, even though we're going to see it's not going to end up working. So I'll explain what this is, explain why this doesn't work. But I wanted to kind of cue up this idea of a reduction because we'll talk about it a lot more later. So the idea here is to change our weighted graph into an unweighted graph. So we know BFS works in the unweighted graph, so could we potentially transform our weighted graph somehow? This idea of trying to do this translation into a problem that we know how to solve is called a reduction. We're trying to reduce a problem that we can't solve to one that we can. Reduction is a bit of a strange term that comes from the computer science field. You probably should just think of it as a transformation, but we call them reductions because you're reducing the problem to one you know how to solve. So here's my idea. Suppose we had this weighted graph. The cost from A to B is 2, from B to D is 1, A to D is 2, A to C is 1, and C to D is 2. What if we somehow expand the graph? So for that, all those edge weights that are 2, we kind of put a dummy node in between to actually add 2 edges there. So now the hope is that BFS would work, because in order to get from A to B, you'd have to go through 2 edges, since we've transformed this graph to have extra edges corresponding to these edge weights. This idea of transforming this graph is the central idea of a reduction. A reduction is changing a problem from one that you don't know how to solve to one you do know how to solve. When we think about problems, you should think about them as kind of living in separate universes. So in one universe on the left, we have this weighted graph shortest path problem. Find the shortest path in a weighted graph. And in this other green, teal, blue world on the right, we have the unweighted graph shortest path problem. And we already know from lecture on Wednesday that we can run BFS on this to find the shortest path. A reduction is these purple arrows, a way of transforming a problem in the problem space that you don't know how to solve into this problem space that you do know how to solve. So maybe kind of doing this expansion of expanding the edges based off their weights. Then just running the algorithm we already know, like BFS, to figure out what's the shortest path. And then the other part of the reduction is now that you know how to solve that kind of fake problem that you just created, can you translate the result back to a result in your original problem space? So can you kind of take that answer from your reduction and kind of work it back? Now, I should mention right now, it's not always going to be the case that one of these reductions exist or even work. So we'll see that in this weighted graph example, this reduction is not going to work. But the idea of a reduction is very clear and very important, which is taking a problem from one space and translating it to one in another space, using an algorithm we already know in that space and translating back. So even though I have hyped up reductions as being this really cool general problem-solving approach, it's not going to work for this weighted graphs case. For example, it's not always possible to convert edge weights to a whole number of nodes. So if you look on this graph on the left here, I have like 1.5, 0.001, or 0.01, 1.8, 9.2. It's not clear how I can expand those into an integer number of edges. And you might be wondering, well, I see all of the numbers there have like at most 2 decimal places, so maybe just multiply everything by 100 and make 1.5 into 150 or something like that. Now, the problem there is not all real numbers can be expressed as integer fractions, for example, pi. So we'd be kind of at a loss here for how to represent this as a discrete number of edges. Additionally, even if we could represent every weighted graph in one of these unweighted expansions, it's not always going to be efficient to do. So for example, if you took this graph on the right and you have really large numbers, then we'd expand this graph into a really, really huge graph. And now this algorithm might run really, really slowly. So our idea then is, even though this reduction won't work here, it's still an important idea to keep in the back of your mind, and we'll come back to kind of frequently. Let's try to change the algorithm, the BFS algorithm, take advantage of these weighted graphs, and we're going to talk about that in our next video.